Greetings, wonderful physics students, and welcome to Physics with Captain Rod. I'm going to make this video to get you started with your Unit 1 homework set, charge and the Coulomb force. So, let's see, number one, consider a small particle. Right, some sort of object here. I'll even start with a picture like I always do. Some sort of object. How many electrons must be removed so that the charge is 2 millicoulomb? Now, milli means 10 to the minus third. So effectively this means 0.002 coulombs. So just a little reminder, how do we charge an object, right? This object presumably is electrically neutral, meaning that it's got the same number of protons as it does electrons. If we removed an electron, it would now have one more proton than it does electrons, and its charge would be plus, I'll just say, 1e, where e, again, is the 1.6 times 10 to the minus 19th coulombs. If we, not much of a 19 there, negative 19th coulombs, good enough. All right, if I removed another electron, right, then the charge would be plus 2e, right, two of these. If I remove n electrons, the charge is n times e, where e is this value. And what we're wondering is how many of these do we have to remove until the charge is equal to this value, 0.002 coulombs. So that's enough to probably get you rolling on that. B, done virtually the same. All right, the charge on this object is going to be n times e, the fundamental unit of charge. Now keep in mind that we are adding electrons here to it. So think about what that's going to do as far as the plus and minus signs on that charge, whether it's going to be positive or negative. That's probably enough to get you through the first problem here. D, where it says explain why the charge on the particle must follow this equation. Charge equals n times e, where e is an integer. Just write a sentence or a paragraph out about why that is. All right, let's talk about number 2 here. Two identical conducting spheres are separated by 60 centimeters center to center. So that means in this problem, that distance right there. Also, the word identical is very important because what that means is we're going to assume they have the exact same geometry, exact same surface area, and so forth. Okay, one carries a charge of 50 microcoulombs. Ooh, I gotta fix that spacing there, but all right, so I'm gonna call that one charge 1, 50 microcoulombs. This one also is charged, a different value. There's your minus 20 microcoulombs. Keep in mind that micro means 10 to the minus 9th. Now, let's see, part A, what is the Coulomb force acting on the sphere? Now, this does say acting on the sphere on the right, right? So acting on this sphere. Now, it's a plus, positive, negative situation. Right, so we're going to get an attractive force between them. Right, and that force is governed by Coulomb's law, which remember is K, Q1, Q2 over distance squared, or I'll just put r squared. These are spheres. It's reasonable to model them as point charges. That's why we're applying Coulomb's law. Now, you're just going to calculate a number, basically. I mean, there's enough values here given that you should be able to do that. Just keep in mind that this says what is the Coulomb force on the sphere on the right. So make sure you include a direction in that when you calculate a number. Let's see, how many extra electrons does the sphere on the right have? Well, just remember that the charge on an object, right, has to follow this. It's got to be some integer number times the fundamental unit of charge, E, 1.6 times 10 to the minus 19th coulombs. Let's see, C, assume they're connected by a wire. Now, let's see, what will the new Coulomb force be? So now, if we connect these by a wire, let me kind of do that in my picture here. I'll use a gray here. Now, a wire is made of copper or aluminum, something of this nature. That's a conducting material. That will allow charge to transfer. Now, think about what's going to happen, and think about the spheres as a system. This system has a net charge that is the sum of these two numbers. And if we connect them by a wire, think about what the charge distribution should look like if these end up identical spheres. That's important for this. So you have to kind of come to a conclusion yourself about what the new charges look like. Then you can recalculate Coulomb's law. And then also decide, will it be a repulsive or attractive force? So I'll let you do that. I'm not going to get into that in great detail. Okay, number 3. Two charged particles carry the same charge. The Coulomb force is measured to be 20 newtons. Answer each question below relative to the 20 newtons. So here's what I mean by that. Let's see. What's the new force if the distance is doubled? So this really is a conceptual question. Remember that the Coulomb force, right, K Q1 Q2 over distance squared. So just ask yourself, this is a 20 Newton force under a bunch of conditions, all of which presumably are known. And then ask yourself, if I double the distance, what's the new force going to be? You should be able to give me a value for that. Part B, what will the new force be if the distance is cut in half? Now, I think when I said relative to the 20, what I mean is this. Question B is not relative to question A. It's referring back to the original. So if we take that 20 Newton force and then we cut this distance in half, what is the new force? That's what that question is asking. And I'll let you answer C and D. Oh, I got to get those on the same page. Whoops. All right, let's chat about number 4. That's one I can see you needing a little bit of help. So 4 is about a little piece of matter. Oops. Let's see, a small piece of copper of 0.5 grams. So I'm going to imagine a piece of copper here, right? We know the mass of it. I don't know if that's going to be relevant or not, but roughly the size of a BB. Now, copper has a molar mass of 63.5 grams per mole. So that right there, you should be able to calculate how many atoms are there. Oh, yep, that's the first question, number 8. Now, each atom of copper has a certain number of protons. You're going to get that by looking for the atomic number of copper. And I don't remember what that is off the top of my head, but you're going to look up the atomic number of copper. And then if you take the atomic number, that's the number of protons in the nucleus, times the number of atoms, you would then have the total number of protons. Okay, how many electrons, assuming a neutral atom? If it were neutral, okay, that's kind of a conceptual question, and you've got the answer to B. Effectively, you should know what the answer to C is. Okay, so part D is kind of a theoretical question. If we could separate all the protons and electrons out of that copper, and we, here's the Earth here, and we put all of the protons at the North Pole. So imagine, we'll just kind of model that like a positive charge. That's all the protons. The charge you're going to get from the number of protons times the charge per proton. Then we've got all the electrons down here at the South Pole. The charge will end up being the same. You're going to get an attractive force between them, and that attractive force, right, we can calculate by Coulomb's law. And just run through and put our numbers here, 9 times 10 to the 9th Newton meter squared per Coulomb squared. Our charges here and here, that you should get the same values. The distance between them squared, so look up the diameter of the Earth in meters. and calculate a value. And I think you'll be pretty surprised when you see that value, and it will tell you something about, I think, the cohesion of matter when you get that number. So, and when you get that, we'll talk about that in class. So that's probably enough on this video. I hope that this has been a reasonable start to get you rolling. Have a great day.